We're here at Google's offices today with Faisal Karjikar to talk about data, data representation, data compression, the whole bits and bytes thing. Faisal, it's great to be here, it really is. Thank you for having us. Okay, so let's start with this notion of digital information. How come computers can only deal with digital information?
So, to really understand why that is, you have to kind of understand what's actually inside of a box or a computer. I use that term because that's what most people think of a computer, but actually the thing you have on your wrist, or in fact, a lot of people's toasters and washing machines are now computers technically. But let's just let's go with the old-fashioned box or a laptop or something. If you were to look inside of it, you'd find there's actually a lot of electronic circuitry, and there's lots of very delicate metallic parts and things that are quite intricate. But what we all know is that at some point we have to plug it into the wall to get electricity, right? And then that electricity courses through it, and then it must be some sort of circuit. And so there's some sort of magic that goes on inside, which can really be explained by electronics and physics and that kind of things. But at the lowest level of those, you have electronic components that can either just be on or off. It looks like it's very, very complicated from the outside because we see it doing all these cool things like whirring and buzzing and somehow we'll be able to output music and stuff. But at the very, very fundamental level, what we have are these circuit boards that are made up of like billions and billions of gates and transistors and all these components that have been welded on and soldered onto the
So this notion of the transistor as something which allows current to flow or prevents current from flowing.
Exactly.
It's essentially one of two states.
It is one of two states. So, or you can have, either on or off, and there is like a slight threshold which allows, the current to dip ever so slightly or go up slightly, and it won't just turn your computer off. So all the components, all the things that you learn at school with and or and all that kind of stuff, essentially takes in zeros and then comes out with ones, or vice versa. So that zeros and ones are the two discrete steps. So there's nothing in between.
All data, all program instructions, everything which a computer works with has to be essentially reduced to this binary form.
So and the word binary, by the definition of it, bi being two, right? It's two. So you can be bilingual, you speak two languages, bipedal, two things. So binary, so it's two numbers. So you have like the 0 or the 1, on or off. In fact, even the symbol for the power on and off is actually a 0
and a 1.
And a 1,
it's one thing or another. Yeah.
Right, and that's all it is. And it is that fundamental thing of computer science, which is that everything is zeros and ones. Okay. Everything you see. So it could be,
So you say this is fundamental about computer science. Is it fundamental? Is it possible to have computer science that doesn't work in a binary representation?
So in the system that we currently work in, it is zeros and ones, but that's a different
present-day technologies with practical application. We're talking about binary.
Exactly. Yeah.
Okay.
So you could do other things, but this is a very kind of common misconception that I've seen is that people think we have a computer and then therefore binary was invented. It actually was not. We had this computer and the system only works with power on and off and states of 0 and 1, and we decided actually binary was the best thing to use to represent that system.
If we go back as far as Colossus, we have light shining through tape or not, and we have relays or valves which are letting current flow or not.
Yeah.
Okay, fine. So we live in an analog world, something with lots of sort of granular detail to it. What do we gain? What do we lose when we move information from an analog realm into this digital, into this binary realm?
So moving it into digital, so converting it from curves into step or square waves, we actually make it amenable to computers to actually handle the process. So
if we want to use a computer to
so
process information, to store information, there is no alternative.
Yeah, so all the benefits that we gain from using computers to analyze it, all the horsepower, all the things that can do faster than us, we can only really do by giving it in a format that it can understand. and it can't understand, analog data and all that kind of stuff. But what we then do lose is that, there is that beauty in a curve which we suddenly have to narrow down into a square wave. And what that means is that it's potentially you will lose some data in that conversion. And if you don't, there are ways to go around that by using a lot more data to describe the information. And so you can try to approximate the analog data as closely as possible. But, and audio is a really good example of this. You can try to get it as close to possible, but
you will
always be,
which is why some folks seem to think that vinyl is still better.
Exactly, absolutely. It's a great example.
Okay, right, thank you. So can we get into the detail of binary representation? Let's start with something very simple like whole numbers. How do computers store and transmit whole number data?
Right, so, and this is again, I keep coming back to this, but it's so fundamental that everything has to be zeros and ones. So words and pictures and everything, so that even the building blocks of what we know as like language and number have to somehow also be stored in the zeros and ones.
And this is down to only being able to store two symbols
at any point. Exactly,
okay.
Right. And so we have 1, 2, 4, 8, and it will just continue on, and we call the right hand side the least significant bit because it's worth the least in terms of value. And then the furthest right would be the most significant bit. So, and just as we would do in our numbers, we would say the number, let's choose a smallish number, let's say 25, we would say, right, 2 in the tens column, and then 5 in the units. Well, we can't do that, or computers can't do that in their base 2 representation. So we have to see, 1, 2, 4, 8, 16, 32. Well, we don't need 32. Well, we can use 16, and we can use an 8, and then we use the 1, and then we put the ones in the right place.
So we're looking at a 1, a 0, a 0, and a 1.
Yeah.
As a binary representation of the same number.
And that's the key. It is not actually 11,001.
No, quite.
Right. Yeah. And that's why, usually when we write these things down, we put a little 2 in a subscript underneath it to kind of tell everyone, actually, this is in base 2.
Okay, so that gets us to whole numbers. What about the real numbers, though? How can we represent any number in a binary form?
So, real numbers, and it's an unfortunate naming, because there's nothing not real about integer numbers. But these are numbers that have a fractional part to them. So the reason is because if you wanted to have a number system that can extend to take up the number of people in the world, so that's like billions, right? Or the distance between atoms, which is also a giant number, but very, very small number. So a very small number, but written out, it'll be very...
Lots of zeros in front.
Lots of zeros in front. And if you want the same number system to be able to do that, if you were just to use a normal numbering system, you'd have to have something that's very wide. To avoid having just so many of these, we use something that's called, scientific notation, or when I was at school, standard form.
Okay.
So
something like the speed of light is 3 times 10 to the power 8.
8, exactly.
I need those 2 bits of information. I need the 3 at the front.
Exactly.
And the times 10 to the 8 to say how far to shift across from the units.
Yes, exactly. The number 2, which we raise, so for example, 10 to the power 8, that's known as the exponent.
Right.
So that's the amount that we need to move the little decimal place.
Okay.
Right.
In this case, decimal.
So the rate exponent. I would use the word rate exponent, it's very technical, but it's the point, but in any base.
Okay.
So it could be a binary point or a decimal point.
It's still after the units.
So just the rate exponent, the point. And that's what tells you to move. The other number, which is the 3, in this example for the speed of light, is what's known as the mantissa, or sometimes also known as significand.
Okay.
So with those 2 information, significand, or mantissa, exponent, you can actually represent a huge range of real numbers. Yes. So
with an arbitrary degree of precision, I guess.
Well, arbitrary up to an extent. So here's the thing.
Semi-arbitrary degree of precision.
Exactly. So There are two ways we could do this. So there are, well, there's actually quite a few more, but the
Okay.
two main ones. Let's say fixed point. So we can say we have 32 bits, which is a very a common number. To say a 32 bits to hold or store a number, right? We can't just give every number as much space as it needs. We give it 32 so we can process it. It's a common word size, although we move it to 64. So 32 bits, and so we say, okay, let's give the last 8 as the
Okay.
thing that comes after the radix.
Yes. Yes.
And then the before is just all the numbers before it, and we might even give that first bit. We might need that for it to be the sign.
Okay.
So we might have 1, 23, and then
So within a 32-bit word,
yeah,
we can split the number of bits across.
yeah.
To say this is for how big the number is. This is the size. Sorry.
Now there are obvious disadvantages to this, right? So we can never get any more than 8
Yeah.
significant sort of figures of precision. So this is where we talk about arbitrary
But this
precision.
gets us quite a large range.
Yeah, so
Real
for
values that we could represent.
absolutely, and for not for most, for many things, this is actually good enough,
Yeah.
right? But this is what we call fixed point. So that we have 8, and that way we know that the radix point is exactly where we left.
Yes.
Now, if we actually wanted to shift that kind of proportion, so instead of saying 24 and 8, actually say, well, I know my number is going to be quite small in terms of the mantissa, and I know actually the part after the radix point, I need it to be very, very, very accurate. So I want to shift it. That's when we use this thing called a floating point. And so we actually want to not have that radix point fixed. We actually wanted to float it along. And that's when we use this idea of the mantissa and exponent to tell us how much to move the radix point along.
Okay, so let's move on to thinking about other sorts of information now. What about text then? How is that represented digitally?
Okay, so text is obviously one of the things that was first thought about. We thought, okay, well, computers need to be able to understand text, so how do we do that? And lots of people came up with different ideas, and that usually doesn't work out very well when everyone can't agree. So one manufacturer's keyboard you plug into a computer, you think you're printing the X, and it comes out with a different thing because it is programmed to understand a different manufacturer's keyboard, and so to avoid that from happening, a convention was called, so all the manufacturers agreed on this thing called the American Standard Code for Information Interchange, which we call ASCII. And that says, the letter A is 64 or 65.
Right.
And
65, yeah.
65. And the capital A, and everything that you see on the sort of on the normal standard.
So we take
keyboard.
characters in the Latin alphabet and a few punctuation, a few digits, and probably some other things, and come up with a number for each of those.
Yeah, absolutely. Well, yeah. So a number which for a computer obviously will be binary. We say 65 because we are talking in denary or base 10. So, but a computer doesn't think of it as 65. So. Similarly, though, it doesn't see it as the letter A.
No.
This is one of
Just
those
a
fundamental
number.
things where it is just the number 65 in binary, and it just has to interpret that as that is just data, and only when we decide that it should be the letter A does it become information useful.
Right.
That
But
that's
that pattern of bits could be the number 65, could be a capital A, could be a tiny part of a picture.
or a video or anything
Program
else.
instruction.
Exactly.
Okay, but ASCII only allows a space for, is it 128 or 256 different characters? There are many, many more characters involved in the world's languages.
So that doesn't leave you room for the various different alphabets all you found all around the world. So let's use more space to be able to describe more different symbols, right? So we can say you can use up to 4 different bytes,
Right.
or and that is a system that we can continually add to because there's just so many potential symbols you can use with these combinations, and that
So not only can we represent Chinese or Japanese characters where we have room for emojis.
Right,
where else
absolutely.
we want it.
Emojis
Yes.
is a great example because they've been added recently
Okay.
to this format called Unicode. So Unicode starts off with the first byte actually being the same as ASCII, and then it's extending. So it allows you to have lots of different what we call code pages, and new things can be added to it as we need. So that everything that you want to be able to transmit and send over and want computers to understand and be able to process.
So it's not just text, but anything that's represented symbolically.
Absolutely, and so at Google we don't use ASCII at all anymore. We just use Unicode because we take input from so many different places
Yes, of course.
that Unicode is the only thing that can be able to describe it all.
What then about other things like images? How do we represent those digitally?
So images are a whole new field in and of itself because in the early days you could just have what's known as a bitmap, which was just if you imagine an image just as a grid, and then each a pixel, each pixel being
Square
the
of the grid,
smallest, the smallest element of a picture, and you can just say, well, if we say, let's say each pixel will give it three bits to kind of give it a color, so that gives us 8 potential colors we can give it, and so we'll just say, right, we'll arrange all the pixels in a line, and we'll say, right, so this pixel here is like 111, and this pixel is 000. So in a file, it would just be like 111,000, etc. And then, the computer would just read it and take the blocks, send it to the monitor display with those colors, and that's what the picture would look like. And if you ask your parents or your grandparents, maybe, in the early days of the internet, that is what the internet looked like. You would wait, and you'd see lines coming as the data get transferred and the pixels
dot
would be.
by dot.
Yeah, absolutely. Row by row, dot by dot, and you'd be able to finally see the picture you want to that you wanted to send. Times have since moved on, so we now have much better ways of even being able to describe things within images.
Sort of vector graphics
Absolutely.
territory, and describe the shapes that
As
make
mathematics.
up a picture rather than the coloured squares.
Absolutely. So we've come across ways of describing the shapes as mathematical expressions that we can then use mathematics on to scale and up and down and without losing any quality. So there's that way of storing images. There's the we can have bitmaps of it, and we can store it that way. So there are other ways of making sure and these are different file formats that you've seen that kind of make sure that the data kind of ends up where you need it to
And
be.
similar issues with sound, or similar approaches with sound.
Absolutely. So sound has its own different ways. So you can take it like in a raw format and just try to, everything that the microphone hears, you kind of just dump into, a sound container, and then the speaker is best to replay it. And that, very much depends on how many, what we say is the sample rate is, how many samples per second you can quickly pull from the microphone and dump into, you can, whether you want to do it that way. But there are other smarter ways of doing it now as well, right? And this is where we kind of move on to real compression.
And I guess video, we take the idea of images and just do that lots of times a second, or is it more complicated?
There is a lot. You could do it that way. And in fact, in the early days, the standard was just having, a JPEG, and the very earliest video was also known as like a movie JPEG.
So I guess movies work pretty much the same way as images, but just storing lots of images for every second of film.
You could just, think of it as lots of still images put together, and in the very early days, that's actually how it was created. So
And much like analog film used to work.
absolutely.
Yes.
So you can, but in that way, if you treat them as individual images, and we'll talk about this when we talk about compression, you actually lose a lot of the ability and flexibility that video allows you to do to make the stills more seamless.
Okay.
So it looks more continuous rather than seeing.
Ah.
You don't want it to appear like lots of static images. You want them
No,
feel like it's just moving, seamlessly.
Okay, so that does make video sound more complex.
It does.
Right, now you mentioned compression
I'm sorry.
earlier. Let's talk a little about that then. What are our techniques for taking large amounts of data, which captures text or images or sound or video, and using less storage for that?
So the thing that we started off with was that everything is in a computer is made up of zeros and ones, right? So what that means is that everything that we want to store in a computer has to be stored in a series of zeros and ones too. And so whether that's a sound, or whether that's a picture, whether that's an image, or a video, or anything that we want to store, is going to be zeros and ones. Now what we can do is take that pattern of zeros and ones and see, okay, is there any way that we can eliminate what we call redundancy in there? And by redundancy, we mean repeated patterns. So if we see the pattern, like 5 zeros followed by 5 ones, etc., in lots of different places.
So in my holiday photographs, I might have large blocks of blue sky up at the top of the screen.
Absolutely.
Or top of the picture.
Yeah. So in that sense, the bit pattern, the representation of it, will actually be very, very similar across lots of places.
Yes.
In the images, it actually works a little bit differently because we look at pixels not as in individual colors, but we actually chunk them up into blocks called macro blocks, usually 8 pixels by 8 pixels wide, and we say, right, okay, what can we do here? And that's kind of known as spatial compression.
Yeah.
Because we look at what's near it, what's around it, how can we absorb the difference, and there's a lot of psychology involved in this, because a blue sky might have a very different, very, very, fine difference in blue that you really can't see so much. So you can actually just average the two colors so they're the same color, and then be able to say, okay, that whole block is just one color.
Yes.
And to the human eye, you don't really notice the difference.
So not only are we using algorithms which look for repeating patterns in these blocks, but we're also modelling how this would be perceived by the average viewer.
Right.
Yes.
So there's this model, right? This like a visual module of
Yeah.
what can the human view, what can the human eye take in, and what can it throw away without us noticing.
Okay.
In this video, for example, right now, we've been moving, but actually the things around us haven't been moving very much at all. So what we can say is between the frames, keep these pixels exactly the same,
Right.
or only move these things. So we can have these instructions, and these things are known as like B frames, or P frames, or I frames in different formats. So we can say, this is an instruction that says, okay, this pixel hasn't been moved for ages, right? So don't do anything to it. Or rotate it, or slightly change the color of it. So we can make sure that, across whole frames, we can save a lot of space. This is, for example, something that YouTube does a lot. For example, if you're standing in front of a room and the 75% of the screen hasn't changed while you speak, there's no reason to keep that data for 75% of that screen for every single frame. And we can, throughout, as the time goes by, the tempo, the longer that stays there, the greater the compression you can have.
Of course, yes.
So there's a lot of different ways here.
And there's a difference between lossy compression and lossless compression.
Absolutely. So lossy compression means that you can never really get back to the original state. You will permanently lose
We'll
data.
never get back to the original analog state, but we can get back to our best ever digital representation.
So lossless,
Lossless compression.
which is what the name suggests, is that we don't lose anything. So
if I take a program file and make a zip file of it, then I need to use lossless
right,
compression. Yes.
because there's an expected structure in there that you need to have when it comes back.
Yeah.
And if that, if you decide to do what we do, for example, with looking at two different colors and averaging them and putting, because they're close enough won't cut it for
So it's code that we're writing. It's got
absolutely.
to be
Like, I think if it's your report, you don't want a file to think, oh, actually, this paragraph is kind of like the paragraph next to it, and let's squish it together, right? You want it to be exactly what you had to begin with. So that's lossless. Lossy is where we throw away data, but we throw away data really sensibly, right? The things that you won't notice. So MP3 is a really good example of this. So MP3 example.
And this can be literally things which no normal person will ever be able to notice.
Right. So, your dog may notice it, but, you won't. So there's this thing called the psychoacoustic model where, things that the human ear won't even detect, it focuses on those bits and then takes them out.
Yes. So, Face, how are you drawing on these sorts of ideas areas in your work here at Google?
So a lot of my projects that that we're launching are actually going out into places in the world which have weakened infrastructure for various different reasons, natural disasters or like political instability, and so they don't really have, for example, a great internet connectivity or infrastructure for mobile internet or anything like that. So what happens in places, for example, in rural India, is that people will buy internet by using a data little dongle. So they will buy 5 GB. So they will go to a shop and say, okay, I want 5 GB, and then they will get a little dongle that they plug into their laptops, and that's it. That's the amount of that's the internet for that they have. That's all they can afford. So you have to be very, very careful of how you use that data. So if if I create a video that's really high quality, but I don't compress it, then that's going to really impact how much data that it requires to transmit that video, and actually he'll find that he'll quickly run out, because then he'll have to buy it again. So we have to be really conscious about this.
As well, storage may be cheap. Bandwidth.
Absolutely.
In all parts of the world certainly isn't.
Certainly isn't, and we work very hard here at Google to make sure that everything we send is as small as compact as possible. So that's something that I work on a lot. So and there's other ways we can do it. Making sure that things are offline, but there are certain things that live online, and for those things that we have to make sure that they're available in very sort of low bandwidth friendly formats.
Thank you, Face. Thank you ever so much for your time this morning. It's been really interesting hearing about this. Thank you so much.
Thank you.
Don't miss out on Computing at School's great content here on YouTube. Subscribe to our CAS TV channel.